high-tech manufacturing jobs, national security, energy costs. These issues impact every American, be it a direct impact as a family cuts back elsewhere to pay their electricity bills, or indirect as job losses in high-tech manufacturing ripple out to further saturate an already far too underemployed workforce. Every one of these issues can be positively impacted by a single technology, a technology which the United States funded research for between 1954 to 1974, a technology neglected and forgotten due to politics and oligopoly interests. In 1974, it was referred to as the Thorium Molten Salt Reactor, researched by Alvin Weinberg and Eugene Wigner. Today, it is often referred to as liquid fluoride thorium reactor, LIFTR. If you're already familiar with LIFTR and want to see the United States retake the lead in developing this critical technology, head to thoriumpetition.com right now. If you'd like to learn more about LIFTR, please keep watching. The internets are no stranger to claims about energy breakthroughs. In fact, often mainstream news gets taken in by unsubstantiated claims.
This will be the replacement for fossil fuel, gas, nuclear, and other forms of energy.
The process uses water, a form of salt, and other common materials to create a chemical reaction they say is 200 times more powerful than gasoline or coal combustion.
LIFTR does not depend on speculative physics. LIFTR was developed in America at Oak Ridge National Labs. So, what is LIFTR and why are people so excited about it? Because nuclear energy has amazing potential.
Nuclear has the advantage that the amount of energy sort of per atom is about a million times better than coal or natural gas. So you start with this huge advantage, and yet the complexity of the plant, the things you have to do, you more than wipe out your million for one advantage. Nuclear innovation stopped in the 1970s.
If we could somehow eliminate all the downsides associated with nuclear energy, then humanity's problems with fossil fuel shortages, pollution, and energy scarcity would all be solved. Of course, it isn't that easy. We are only capable of converting a handful of elements into energy by breaking their atomic bonds: uranium, plutonium, and thorium. And today's reactors succeed with a particularly rare isotope of uranium, uranium-235. Most of the uranium mined for fuel cannot be used in a reactor because it is uranium-238.
Can you imagine burning platinum for energy? I mean, that would just be nuts. We're burning this extremely rare stuff.
For every unit of useful uranium-235 mined, 300 times as much uranium-238 has been refined, extracted, and left over. LIFTR's fuel is thorium, not uranium-235. Thorium is 400 times more common than uranium-235.
In the United States, we have over 3,200 metric tons of thorium that was stockpiled 50 years ago and is currently buried in a shallow trench in Nevada. This thorium, if used in lifters, could produce almost as much energy as the United States uses in 3 years. And thorium is not a rare substance either. There are many sites like this one in Idaho, where an area the size of a football field would produce enough thorium each year to power the entire world. It's so energy dense that you can hold a lifetime supply of thorium energy in the palm of your hand. We could use thorium about 200 times more efficiently than we're using uranium now. Because the LIFTR is capable of almost completely releasing the energy in thorium, this reduces the waste generated over uranium by factors of hundreds and by factors of millions over fossil fuels. We're still going to need liquid fuels for vehicles and machinery, but we could generate these liquid fuels from the carbon dioxide in the atmosphere and from water, much like nature does. Imagine carbon-neutral gasoline and diesel, sustainable and self-produced.
The research documents are all public domain and available online. Lectures detailing the science behind LIFTR are available for free on YouTube. China is currently investing $1 billion to leverage the United States' past research in this technology to secure future innovations as intellectual property of China, and plan to see it commercialized in 20 years. So, if LIFTR is so great, how come you've never heard of it?
The presentation today from Kirk Sorensen. This is a technology that's been around for a long time, since shortly after World War II. If it's such a great idea, why aren't we doing it?
The monies that had been appropriated, the red line shows the expenditures on the fast breeder reactor. And this graph only begins in 1968. At that point, the United States had already built several fast breeder reactors. It's very hard to see the green line for the molten salt breeder reactor technology. It's extremely low, and then ultimately it was canceled.
Mr. President, since you missed our meeting when we had on breeder reactor, you know, I wanted you to know that we sent the message today, Craig, but that I just told Ziegler that it's got to be something we play very close to the vest. But I am being ruthless on one thing. Any activities that we possibly can should be placed in Southern California. On the committee, every time you have a chance, needle them. Say, where's this going to be? Let's push the California thing. You do that?
I'm so delighted you released that $16 million on the enriching complex.
Good.
That handles a bad blood problem for us.
Right, good.
Nixon was from California, Hosmer was from Southern California. Holofield, Chet Holofield, who ran the Joint Committee on Atomic Energy, was also from California. It doesn't lead me to believe that the president was seriously considering alternatives to the fast breeder reactor and other paths that could be taken. It was a focus on what can we do right now to get jobs back home to the folks who are going to support us in re-election.
Now, don't ask me what a breeder reactor is. Ask Dr. Schlesinger, but don't tell him not to tell you, because unless you're one of those PhDs, you won't understand it either. But what I do know is this, that here we have the potentiality of a whole new breakthrough in the development of power for peace. And that means jobs for this area, but jobs and power for hundreds, for millions of people all over the world.
A lot of the people in the background there probably had PhDs in nuclear engineering and knew exactly what a breeder reactor was. But Nixon was emphasizing the economic benefits to them of his announcement that there was going to be a breeder reactor.
All of this business about breeder reactors and nuclear energy and the stuff is over my head. That was one of my poorest subjects, science, and I got through it, but I had to work too hard. I gave it up when I was about a sophomore.
Maybe it might have benefited our country a little more if Nixon had been able to ascertain the different values of different types of breeder reactors and why one might have an advantage over another. Testimony given in September of 1972, they noted that the U.S. government would be expected to cover cost overruns on the breeder reactor, and the development cost would go over $700 million. At this point, industry had already committed $200 million, these are then-year dollars, to the breeder reactor effort. Representative Craig Hosmer, who was the fellow on the phone call that we heard earlier, said that if cost targets were missed, I, for one, don't intend to scream and holler about it. In that same month, the Atomic Energy Commission issued WASH 1222, which was an evaluation of Weinberg's molten salt breeder reactor. It almost completely ignored the safety and economic improvements possible through the use of the molten salt breeder reactor technology. Weinberg himself had a meeting with Chet Holofield and Milton Shaw of the Atomic Energy Commission. Milt was like a bull. He enjoyed congressional confidence, so his position in the AEC was unassailable. And it was clear that he had little confidence in me or Oak Ridge. After all, we were pushing molten salt, not the fast breeder. More than that, we were being troublesome over the question of reactor safety. He had invented the pressurized light water reactor. Here's a picture of some of the pressurized water reactors. His work on the thorium reactor led him to believe that a significantly higher level of safety was possible. And this, in large part, was because the thorium reactor operated at low pressures, whereas water-cooled reactors operated at high pressures. So he was beginning to bring these issues up. Congressman Chet Holofield was clearly exasperated with me. And he finally blurted out, "Alvin, if you're so concerned about the safety of reactors, then I think it might be time for you to leave nuclear energy." A very sad moment in the history of our country and probably in the history of the world, because an entire direction of potential development was being ended at that moment by a not well thought out comment by Congressman Holofield. In January of 1973, Oak Ridge was directed by the Atomic Energy Commission to terminate the development of the molten salt reactor. And nobody, as far as we know, in D.C. ever revisited the question of was it a mistake to cancel the molten salt reactor effort? Should we have gone back and said, you know, now that we're not going to do the fast breeder, maybe we should have done the molten salt breeder reactor? In all of my studies, I have not been able to find any indication that that ever took place, that there was a true revisiting of that decision to shut down and a rethinking. The team that worked on this at Oak Ridge disbanded and dispersed, and over the decades that followed, the knowledge was slowly forgotten.
and it wasn't until 2006 that these documents were posted online for everyone to see.
In early 2010, EFT bloggers noticed that all these guys from China signing up from Shanghai, Beijing, and they started asking questions about this and that.
They went to Oak Ridge. They took them around the lab and showed them everything. And it's funny going to Oak Ridge because they're all about the info and the nano and the bio. And you want to go, what about the nuclear? They never talk about that part, you know. Well, they get to the end of the trip, and the Chinese official, his name was Dr. Zhang Mingheng. Interesting about Dr. Zhang Mingheng, his father was Jiang Zemin, who used to be the premier of China. So this is not a poorly placed guy in Chinese society. So they get to the end of the meeting, and I'm told, Oak Ridge people said, well, you know, we had this great trip. Have you learned what you wanted to learn? And they go, we're actually here to learn about the molten salt reactor. See, we're going to build one. We've already got a site picked out, and we're going to have it built by 2020, and we're here to learn everything we can about it. And the Oak Ridge people were like, huh.
We can be competitive with China on making patents on things that weren't thought of in the 50s and 60s. But if we wait, Americans, Canadians, Brazilians will be buying lifter and molten salt technology from China and paying them the royalties.
Put development cost and unit cost in separate categories. You know, it's like you build a fighter and you spend billions of dollars to design it, but then you run off copies for $20 million a piece. You know, that's how they build like 737s or other airplanes. If you want to go, well, what's the unit cost going to be? There's reasons to think this is going to be a lot less expensive than what we have today if we set the development in another column. And the reason why, number one, low pressure operation. That's the biggest one. When you don't have to have 9-inch thick steel pressure vessels, huge concrete containments. Number two, you don't have to fabricate fuel. You don't have to enrich it, you don't have to fabricate it, and you don't have to have the approach to disposal that we have today. So those two features right away are a big deal. But number three is the safety systems. High-pressure water-cooled reactors have an abundance of safety systems designed to always keep the core covered with water. So if one system has 99% reliability, well, you need another one that also has it so that you can get 99.99, and you know, maybe statisticians will get mad at me, I might be doing it wrong.
It's walk-away safe. Reactivity is stable because as the salt heats up, it expands, pushes some of the critical material into the pipes and tubes out of the critical area, and the reaction slows down or stops.
There is almost no volatile fission products in the salt. All these accidents, Chernobyl, Fukushima, it's the volatile things that'll go off into the air and spread out. That's the real issue.
If the salt is somehow ruptured onto the floor or into the environment, it becomes slowly a glass-like substance.
Even a terrorist attack, a missile strike, etc., you might splash some salt around, but it basically lands and hardens, and very, very little will come out of it.
At every step, Lifter beats today's reactors, with lower cost and greatly reduced environmental impact.
The real challenge with spent fuel management is the presence of those transuranics, plutonium, americium, curium. We don't form those transuranics. We burn up essentially all of the fuel in this process. General idea is you don't want uranium or thorium or anything else to end up in your waste stream, and that's a pretty straightforward proposition in this fluid-fueled reactor. So our waste story is a lot different. Out of about 1,000 kilograms, about 15 kilograms of plutonium-238 will be left over. Now this is good stuff. NASA is desperate for this stuff. Plutonium-238 is different than plutonium-239, the stuff we use in bombs. In fact, it's worthless for bombs. These radioisotope thermoelectric generators are based on plutonium-238, and this is the only way that we've been able to explore the outer solar system. The United States is unique, the only country in the world that has sent space probes beyond the asteroid belt. And it's all been based on having this technology. Short answer, we're out of the stuff. It's gone. We've used it all up. The Russians used to sell us some. They've sold us all their inventory. It's gone. NASA's got billions of dollars of deep space missions hinging on having enough of this stuff to run the batteries to let the thing call home. We will be able to make this in Lifter. If you've heard sometimes about us saying we burn up 99% of the fuel and there's 1% left, the 1% left is that stuff. And it's worth almost as much as the stuff we burn up. In addition, it would make medical molybdenum-99. We are about to shut down the one reactor in Canada that is making molybdenum-99 for medical purposes in 2015. There are hundreds of thousands of patients that will not be able to get their molybdenum-99 that they need for diagnostic procedures when that happens. We can make molybdenum-99 just in normal course of operation, and we can remove it very easily.
Can we undersell coal? The MIT report says capital cost for coal plants new today is about $2.40 a watt, 2 cents a kilowatt hour just for the coal fuel. So this says electricity is about 5 cents a kilowatt hour. In the Lifter case, we're looking at a little less capital cost than a coal plant, fuel cost being negligible, or a total cost of about 3 cents a kilowatt hour. So yes, Lifter can undersell coal.
The promise of energy independence has been made by the last 8 American presidents and President Obama. Today, solar and wind are often touted as the solution, but it must be recognized these are intermittent sources of energy. The sun sets, the wind stops blowing. Often these cycles are very different from demand cycles.
Today, even if they gave you the panels for free, the installation costs make you non-competitive. You know, wind has to be subsidized by about a factor of 2, solar by about a factor of 5, and that's only when they're just a small percentage of the power. When they get to be any meaningful percentage, that's where the problem of their intermittency becomes overwhelming, and you can actually spend way more to try and solve that problem than you spend on the overpriced stuff to begin with. All the batteries we make could store less than 10 minutes of all the energy. We need a big breakthrough here, a factor of 100 better than the approaches we have now.
Use renewables where it's intermittent power from multiple sources.
Okay, there's going to be a wind farm here, and there's going to be a solar array here, and there's going to be a wind farm over here, and one of these 3 at any time will be working, but we'll have power transmission lines to all of them. It costs too much money. People who propose that haven't run the numbers. People don't want to see power plants, power transmission lines. They will fight tooth and nail against power transmission lines.
Today we're putting overwhelmingly 90% of the subsidies are on deployment. This is true in Europe, it's true in the United States, not on the R&D piece. And so unfortunately you get technologies that no matter how much volume you buy of them, there's no learning curve that takes that stuff and makes it economic. They just buy as much as you want, it's not gonna happen. You need fundamental breakthroughs, which more come out of basic research.
Congress is broken along party lines. Can we realistically expect funding into basic research and development? Ideologically, the left wing favors funding basic R&D. They recognize tomorrow's commercial breakthroughs depend on today's smart investments. Ideologically, the right wing favors cutting regulation. Thorium regulation is in need of a reassessment. In many ways, thorium is like uranium. They are both found throughout the Earth's crust, but are not homogeneously distributed. At natural densities, they are completely safe. Uranium is already sought as fuel for nuclear reactors, so despite the regulations surrounding refined uranium, there is already an economic case for mining and selling it. Thorium, however, has limited use outside of a liquid fluoride thorium reactor. If this petition was strictly concerned with America's ability to achieve energy independence, this would not be worth focusing on. However, thorium regulation indirectly impacts America's ability to compete in the high-tech manufacturing sector.
Older folks like me will recall a day when earphones didn't look like that. The whole trick has been the invention of a little magnet based on neodymium iron boron magnets. Extremely powerful magnets, and they use a rare earth mineral called neodymium. So naturally, global demand for neodymium has gone. And because neodymium iron boron magnets are so powerful, one of the places they find application is in the generators that sit on top of windmills. Currently, it's all being mined in China. Now, why am I talking about neodymium? Well, because thorium is always found with heavy rare earth elements. If you remember your periodic table, the lanthanides, that column above the actinides, those are all the rare earths.
Thorium policy in all Western nations undermines a successful development of a domestic rare earth market. All of the rare earths that most Western mining companies are willing to process, they select these rare earths not because of the high ratios of rare earths, but simply the absence of thorium. Thorium just literally drops out like a rock and you have it. So what happens all across America, Canada and South America, there are beautiful monazite deposits that have heavy rare earths that could be very commercial except for the thorium content.
Heavy rare earths are found in iPods and iPhones, hybrid car batteries and wind turbines, handheld GPS devices, and military guidance systems. China has a near monopoly on heavy rare earths.
First, China provided rare earth elements very cheaply to everybody in the world by their cheap labor, lack of enforceable environmental regulation, and their appreciated currency.
Essentially consolidate, control the rare earth market.
And then they said, well, now all of you are coming to our door to buy our rare earths. We don't want to sell the raw material anymore. Our manufacturers can buy it cheaper than your manufacturers,
They imposed a huge export tax on rare earth elements, and so one had a choice to accept a huge tax and increase in the price of the product, or to relocate factory into mainland China and buy rare earth elements on a local market without tax.
It's a strategy, and it's working pretty well.
Manufacturers which use rare earth elements in their products located their manufacturing base inside China. The jobs in manufacturing transferred from the United States and Western Europe into the Chinese mainland.
If Toyota really wants to build a million battery packs, in the end, if they don't find a solution to the heavy rare earth problem, they'll be building them inside China.
If today it is politically impossible to fund lifter research, then we should focus on thorium regulation reform. It is absolutely imperative that we, as a society, take steps to realize the enormous potential of thorium, both economically and environmentally. Anyone watching this video wondering, what can I do to help America achieve energy independence and curb carbon emissions? Sign the Thorium Petition. This brings Lifter to the attention of the Obama administration. Will they fund Lifter? Will they reform thorium regulation? If not, why won't they? Tell your friends about Lifter. In 2006, practically nobody knew about Lifter. Since then, we've seen coverage in Wired and Vice. Thorium symposiums have taken place around the globe. Technologists are on top of this, even if our politicians are not.
I mean, we were working on this stuff a long time ago. We made great progress on it. We set it down in 1974 for kind of dumb reasons, and I think it's high time that we pick that thread back up again.
Here's this amazing work that was done before I was even born. Other people who are a whole lot smarter than me have looked at it and said, this looks pretty darn good. Why aren't we doing this?
How long do you think it's going to take?
At the rate we're going now in the United States, it'll never happen, but that's going to change. Yeah. We're going to make it happen.
China can move fast on this because their politicians often have backgrounds in engineering and science. They understand exactly what is at stake. Clean, inexpensive, abundant energy. If you haven't signed the Thorium Petition, please do so now.